Good morning, everybody. My name is Longfei Chen from Tsinghua University, and I'm presenting on behalf of the original author due to some travel conflicts. Today, I will talk about how to enhance fuzzing with data coverage. Code coverage is an essential part to software testing. In any case, code must be executed to trigger the underlying bug. This is particularly important in the case of guided fuzzing, a type of automated testing that identifies potential bugs and vulnerabilities by maximizing code coverage with novel test cases. As the figure shows, the fuzzer first picks an input from the corpus, then mutates it to generate a random new test case. The program, instrumented with code coverage, runs the new test case. After collecting the code coverage for the execution, the fuzzer analyzes for new coverage and saves the input to the corpus if the execution reaches more coverage. However, there are problems when applying code coverage to real-world fuzzing. One common problem in fuzzing is constraints. For instance, consider the execution flow of an artificial XML on the left. It first reads the header of the input and then checks if the input is invalid by comparing the header with a predefined string. If the string comparison fails, then the parser directly discards the input and exits. In this case, code coverage doesn't provide any information to help solve the constraint. The fuzzer has to blindly generate more inputs. However, the string contains 5 characters, which maps to 40 bits of information. Blindly generating new inputs is unlikely to resolve the problem. So technically, constraints can be solved with concolic execution. Concolic execution represents the constraints as symbolic expressions, enabling solvers such as SMT to solve them. We can represent the input bytes as a sequence of 8-bit vectors. As the program executes, we generally update the symbolic representation of all values based on the input x variables. To solve the constraint, we add an assertion that mandates all bytes to be equal to the expected values. By querying this assertion, we request the SMT solver to provide concrete input values, sacrificing the constraints. However, since the solver can only process one query at a time, yet there are exponentially high number of passes. The classic pass explosion problem can lead to throughput issues at real-world cases. Moreover, collecting constraints and solving also incur high overhead at runtime. Intelligent branch solving can solve constraints with heuristics. For instance, to solve the branch, we can record the operands of the field comprehension with instrumentation. Based on the comprehension log, we match them against the input data. In this example, we found that the first 5 bytes of the input impact a branch and are expected to be less sign, question mark, x, m, and l. Therefore, we can simply replace the bytes with the expected value to solve this branch. However, this approach requires designing tailored instrumentation for individual programs. For instance, rather than instrumenting individual branches in a program-agnostic manner, AFL++ hard codes a curated list of comprehension routines and treats each invocation as an abstract branch. Obviously, this approach doesn't scale. More interestingly, not all program constructs that are difficult to test with code coverage can be solved with constraint solving. Let's consider the case of complex parsers. For example, libpcap supports customized packet filtering with user-provided expressions, which is implemented using a flex-based lecture and a Bison-based parser. The lecture encodes the complex transition table in constant arrays and drives the machine using simple logic. For code coverage, the simple logic can easily result in accelerated code coverage on the left and coverage plateau on the right, providing no useful signal for fuzzing as a result. For constraint solvers, since lecture logic doesn't fit the constraint-based model, leading to problems such as failed symbolization of memory exercises. In short, while code coverage has proven to be useful feedback for fuzzing, it has inherent problems. However, constraint solving is not a panacea. It can't fully resolve the challenges in code coverage-guided fuzzing. In essence, there's a mismatch between the program constructs and the model of the constraint solving. So here comes the question. Are there any other solutions to enhance guided fuzzing? So as Nicholas Birch pointed out, algorithms plus data structures equals programs. In other words, programs are concrete formulations of abstract algorithms based on particular representations and structures of data. This can also be seen from the perspective of programming language implementation. When a compiler converts the source code into machine code, the algorithms are transformed into machine instructions, while the data structures are encoded as constant data. From a theoretical perspective, code coverage is not sufficient to fully reflect a program's semantics. What if we also account data for coverage tracing? So let's see how our design assists fuzzing with data coverage. First, before fuzzing begins, we perform static analysis and instrument potential data exercises. To remove unnecessary instrumentation, we divide data exercises into 6 categories and instrument them differently. Second, during fuzzing, when the data exercise is intercepted, the runtime library translates the different kinds of data exercises into terms of address and length. We store the normal ones in a normal site for further inspection. Third, after the execution of a test case, the fuzzer checks the normal data coverage set. Code and data features are used to jointly adjust the fuzzer's exploration direction. According to the definition of constant data symbols, data coverage can have varying granularities, such as variable, array, field, or bit coverage. Similar to code coverage is function, line, and branch coverage. However, a trade-off exists between the precision of the data coverage measurement and the overhead it introduces. For instance, achieving perfect data coverage would require symbolizing the program's address space into a bit vector and collecting the constant data symbols that contribute to the program's output. While this would provide highly precise measurements, it also significantly slows down the program's execution and reduce the overall fuzzing throughput. To reduce the overhead, we characterize a program's data exercise behavior into 6 categories and use different strategies to collect the coverage. Below are some interesting designs that help us to achieve this goal. Please consult our paper for more designs and the detail for each design. So the first one is load filtering, which helps us to reduce the scope of coverage collection and focus on static values only. Specifically, we obtain the process memory layout with the help of the dynamic linker and compute the address range which belongs to the main binary. This filter allows us to quickly remove load instructions to the stack or the heap. The next design is estimating the address for immediate values. Since they are usually embedded in machine code, it is costly to precisely get their addresses. Observing that instrumentation stage inserts a call instruction to the runtime library, we can directly read the return address from the stack. While the return address is not exactly the same as the address storing the immediate value, it is a good estimation for fuzzing use. The last design that we would like to highlight is refinement-based corpus update. Data coverage is a fine-grained feedback. The space of data coverage is much larger than code coverage. If we blindly save a new test case on novel data coverage, then the corpus may contain too many cases. So our solution is to introduce a replacement-based corpus update algorithm, which only keeps the test case with the maximum data coverage. when multiple test cases share the same code coverage. For example, for the same static value, if the new data exercise reads 8 bits, while the old one reads 7 bits, we directly replace the 7-bit seed with a new one. We implemented our approach based on LLVM's libfuzzer and named our work WinFuzz. We used the classic code coverage approach and evaluated with using FuzzBench's default setup for fairness. Data coverage significantly improves the overall fuzzing performances. It improved the code coverage of libfuzzer by 14%, lifting it to the first place in coverage score and the second place in average ranking. On average, WinFuzz only required 2.96 hours to achieve the same level of coverage as libfuzzer, which takes 23 hours. The execution overhead of data coverage doesn't affect end-to-end fuzzing performance, even for short trials. In fact, data coverage yielded the highest coverage score in the shortest 15 minutes evaluation. However, it did result in a reduction of throughput by 34%. This decrease is primarily due to the added overhead of collecting static values, which increases the execution duration of 26%. As for the increasing in corpus size, among all trials from the FuzzBench experiment, WinFuzz discovered 139%, 150%, 159%, and 173% more seeds than libfuzzer at 1 hour, 6 hour, 12 hour, and 23 hour respectively. So this indicates a substantial linear growth pattern rather than exponential explosion, suggesting that WinFuzz effectively balances between the depth and the breadth of state exploration. So in short, this paper explored how a data-centric view helps fuzzing. For real-world usages, we also explored virus optimization, which helps to reduce overhead for more fuzzing throughput. We also implemented and evaluated our work with source code, datasets, and evaluation reports publicly available. So since I'm not one of the authors of this paper, please direct any question to the authors via email for some details. Thank you for your understanding, and thank you for listening.